So, having motivated the inclusion of the higher order Feynman diagrams into the tree level Lagrangian for the effective description of the motion of the particles in the system, we are left with the issue that what decides on the inclusion of the diagrams for a particular process or a particular effective Lagrangian. In other words, inclusion of this diagram plus this diagram plus this diagram, those are effectively odd in the external lines, in the number of the external lines, and the external lines here are basically photons. So, what dictates whether these particular diagrams should be included, remain, or they should not be included? The last diagram that I have drawn over here actually corresponds to is a endpoint function. That means there are n number of external lines, those are attached to the loop that I have drawn. This particular logic sometimes are called the discrete symmetry arguments that decide whether a diagram with odd number of external lines or even number of external lines should actually contribute to the effective Lagrangian. And these symmetries are sometimes called symmetry of under charge conjugation, parity reversal, or time reversal transformations. So, how does this symmetry operations defined? They are defined in the following way. You start from the last line. If I have in some function an argument which is made up of time denoted by small t, and I make my time go to minus of t, then I would say that on my function f I have made a time reversal transformation. So, t goes to minus t. In other words, suppose I have a line drawn, my t is increasing towards right. Now, instead if I define that my t should actually increase towards left, that means actually what I have done is I have taken t to be equal to minus t, and if my function f and for my function f of minus t does not change from each other under this transformation t going to minus t, then I would say that this function f is time reversal invariant. All right. Similarly, suppose I have a function g of x and I make a transformation that takes my x to minus x such that my g of x becomes g of minus x after this transformation, then I would say that my function g is invariant under this operation x going to minus x or parity transformation. It is invariant if g of x and g of minus x are the same. If it does not happen, if the same thing does not happen, so if g of minus x picks up a negative sign, let us say, then we would say that g of x is not invariant under the operation x going to minus x, or g of x is non-invariant under x going to minus x. So, these two operations, parity transformation and time reversal, they are defined the way just we have told here by this transformation under which the argument of the functions go from x to minus x or t to minus t. So, like this particular function g or f, if our quantum field theoretical or component mechanical arguments sustain these transformations of p going to x going to minus x or t going to minus t, we say that my amplitudes are invariant under time reversal and parity transformation. There are specific operators depending on the kind of theory that we are doing that deals with either spinors or tensors or scalars or vectors, that with a specific structure that gives or defines parity on time reversal. But even without going into these details, in a most elementary form of explanation, we can say that x going to minus x and t going to minus t are good enough to describe our these two reversal transformations. So, having talked about these two, next we should go and talk about the third thing or third symmetry, which is called as charge conjugation. The last two that we have just discussed here, they form an integral part of something called Lorentz group, but we won't be talking about that over here. So, we have now come to the condition of how to figure out charge conjugation operation. In simple terms, this particular operation of charge conjugation means, suppose I have an object over here drawn in red and it has a positive charge. I define it by plus sign. The magnitude of the charge is, let's say that it is q. Then when you say that you have performed on this an operation which is called charge conjugation operation, then after charge conjugation my q should acquire, instead of positive sign it should acquire a negative sign. However, the magnitude that we are talking about should remain invariant. So, the charge conjugation operation is associated with q going to minus q. That is a charge conjugation operation. Now, note here there is something which is very important, that this quantity that we have defined here q is not associated with any one of the coordinates like spatial coordinate or temporal coordinate. Here they form an integral part of something called Lorentz group, but we won't be talking about that over here. So, we have now come to the condition of how to figure out charge conjugation operation. In simple that we have defined over here, we have to find out that under charge conjugation what are the variables that change their sign. For the kind of system that we are dealing with, the variables those enter into the description are important variables. Those are what we call otherwise the vector potentials. Those have 4 components, and these 4 values that mu can acquire from 0 to 3 defines these 4 potentials. So, this A mu that I have defined over here should have on it some variable signature of charge transformation or charge conjugation. So, how do we find that out? To figure that out, you recall that suppose let us take a capacitor plate and let us take another capacitor plate. So, in these two capacitor plates, suppose let us put some charge plus over here and some charge minus over here, and then we ask what is there in between these two plates. Will immediately answer me that okay, there are electric fields. That electric fields, depending on your convention, you might decide that E goes from the plus to minus or minus to plus. So, if I do some charge conjugation operation on these capacitor plates, they are not really looking like a capacitor plate. So, let me give them a look under which they look a respectable capacitor plate, and the battery has done its job. So, now what we do is we reverse the polarities of the battery. So, that means we had a minus and we had a plus here, we reverse them. That means we take the plus over here and we take the minus over here. Then what will happen? What will happen can be drawn over here, that these capacitor plates do not change their place, but what happens is the electric field which was from left to right now goes from right to left. So, what we can say is under charge conjugation E actually goes to minus E. E goes to minus E is what happens. So, what is the effect of E going to minus E? If we say that okay, this is the effect what happens on E under charge conjugation, then we see that E is basically given by minus gradient of the scalar part of the 4 potential times del T of A. There is a vector potential spatial parts, and if E has to go to minus E, then all that we should do is change our phi to minus phi and A to minus A. Okay. So, phi going to minus phi and A going to minus A is good enough to reverse the polarity of my capacitor plate, and it is good enough to change the direction of the electric field. So, I can push forward this argument to say that my charge conjugation operation, if I define this by C mu C inverse, then my A mu vectors should go to minus A mu. That is, A undergoes a transformation by picking up a negative sign. If we have understood this much, then we have been successful in our endeavor to understand the deeper meanings to these operations in a simplified language. Now, as a matter of fact, whenever I am drawing or you are drawing or someone is drawing a Feynman diagram which is having n number of vertices, then what it means is each one of these vertex are carrying an external momentum of order k1, k2, k3, k4, kn, depending on the nth order diagram or n-point function. Now, this operation of charge conjugation that we just have described over here, it holds good whether k is tending to 0 or k is tending to infinity. The events where this magnitude of the photons momentum tends to infinity is called hard, and if the magnitude of the photons momentum tends to 0, then it is called soft or ultra soft. Now, interpolating between these two limits, hard and soft, the charge conjugation operation keeps its identity intact. There are no changes there. This we should remember when we move on to the next item. Thank you.